Hello again. In this chapter we are going to talk about capacitors. Now up to this point we covered 3 chapters. In the first chapter we talked about the electric force, and by the use of electric force we defined the electric field, and then we discussed how we can calculate the electric field for a collection of point charges or charge distributions, the most direct way, which is basically the integral method. And then in the next chapter we talked about Gauss's law, and we went over how we can employ Gauss's law to calculate the electric field in case there are some symmetry associated with the problem. And in the last chapter we introduced the concept of electric potential, and I think we are at a point now where we can discuss some of the applications of what we learned so far. And the very first application that we are going to discuss is the capacitors. Here you see some capacitors in different shapes and sizes, and some of them looks very complicated, but in reality they are very simple devices. So let's first talk about what a capacitor is, and then we will move on from there. A capacitor is actually a very simple device consisting of 2 conducting plates that are separated by a small distance, and the space between them is usually an air gap or vacuum, or sometimes we even fill it with an insulating material. And when you fill it with an insulating material, what you can do is you can even roll it up like this to save some space in your circuit. And we use these capacitors to store energy in the form of electrical potential energy, obviously, to use at a later time. One example I can think of is the camera flashes in those professional cameras. So what you do there is you store energy in a capacitor and you release that energy very fast, creating very bright light for a very short amount of time. But how can we store energy here? Well, you know from our discussions in the previous chapter, when you bring 2 charges close to each other, you store potential energy in the 2-charge system. So the same can be said here. So if you place charges on this plate and on this plate, you have a bunch of charges close to each other, meaning you stored potential energy. So the question becomes how we can store charge on these plates. And this can be done easily with a battery. So if we connect the battery to the plates of a capacitor, let's see what happens. Now we initially have a capacitor whose plate has no net charge, and we have a battery here. Now the batteries, we are going to discuss them in much more detail in the upcoming chapters, so I'm not going to go into too much detail here, but it will suffice to say that the sole purpose of a battery is to keep a constant potential difference between its terminals. So we have apparently a 12-volt battery here. So no charge here, the circuit is not connected yet. So when we turn the switch on, what will happen is there will be a charge transfer between the plates of the capacitor and the battery, and the reason behind that is actually the potential difference. Now remember what we discussed in the previous chapter. So if you have some positive charge in a region where the electric potential is changing, that positive charge will go from higher potential to the lower potential, and if you have some negative charge, then that negative charge will go from lower potential to the higher potential. Initially, the positive terminal of the battery is at a higher potential than this plate of the capacitor. So if it were the positive charges that were free to move, they would move from higher potential to the lower potential here. But in reality, we know what happens. It is the electrons, the negative charges, that move. So the electrons here will go from lower potential to the higher potential. So as they do though, they will leave positive charges here. So you will start to accumulate positive charges on this plate, and what will they do is they will attract the negative charges to the neighboring plate. So you will have positive charges here and negative charges here. And this charge transfer will continue between the plates of the capacitor and the battery until this plate reaches the same potential as the positive terminal, and this plate is at the same potential as the negative terminal, meaning the potential difference between the plates of the capacitor will be equal to the potential difference between the terminals of the battery. From that point on, there will be no more charge transfer. At that instant, we say the capacitor is fully charged. Whenever we study circuits, we usually use a circuit diagram such as this one, and in a circuit diagram we use different symbols for different circuit elements. For example, for a battery we use this symbol, which has two legs, one long and one short, and the long leg represents the positive terminal of the battery and the short leg represents the negative terminal of the battery. And for a capacitor we usually use this symbol, which has two equal length lines like this. So whenever you see this in a circuit diagram, you know that we have a capacitor there. And since this guy is connected to a battery as such, this has to be the positively charged plate and this has to be the negatively charged plate. Sometimes though, you might come across a circuit diagram where a capacitor is represented like this, which is still a capacitor, but these guys represent a specific type of capacitor which are called electrolytic capacitors, and you have to connect these in a specific way to a circuit. It has to be always this terminal that is at a higher potential than this terminal. But apart from the way you connect these capacitors, they behave the same way, so we are not gonna really discuss this anymore during the remainder of this course. We will just stick with regular capacitors. It was shown experimentally that the charge stored on a capacitor is directly proportional to the voltage across it. What we mean by voltage is the potential difference between the plates of the capacitor. And when you have a simple circuit like this, when the capacitor is fully charged, the voltage across it obviously going to be the voltage of the battery. The simple equation that describes the capacitors is then Q is equal to some proportionality constant times the voltage. This proportionality constant is called the capacitance of the capacitor, and it has the units of farad. 1 farad is nothing but coulombs per volt. The unit farad is actually somewhat of a very large unit, and typically the capacitors come with capacitances in the range of couple picofarads to couple thousand microfarads. And it's called capacitance because it tells us how much charge we can store on a capacitor per volt of a potential difference. C changes from capacitor to capacitor, and it depends on the geometry of the capacitors, as we will see later on. So let's not waste any more time and see how we can determine the capacitance of a given capacitor. One way to determine the capacitance is to do it empirically with a simple experiment. In this experiment, what we can do is we can apply a voltage across the capacitor and measure the charge. And we will repeat this for different voltages. And at the end, what we are going to have is different charge values for different voltages. So we can plot a graph of charge versus voltage. And since charge is linearly proportional to voltage, we will get a straight line as our graph, and the slope of this straight line will be our capacitance. This is one way to determine it, and if you know the geometry of the capacitor, we can do this analytically as well. What we need to do is first we will place the charges Q and minus Q on the conductors, and then with these charges on the conductors, we are going to have to find the voltage between the conductors, the potential difference between the conductors. For this, we can use this expression. Remember, potential difference. By the way, this is going to be equal to the electric potential at the conductor which has the positive charge minus the electric potential at the conductor which is negatively charged. And this is going to be equal to from negatively charged to the positively charged conductor E dot dl. Now I am always calculating V plus minus V minus because I want this voltage to be positive. Now in order to calculate this, however, I need the electric field, and I only need the electric field between the conductors. So maybe I should put a note here, between the conductors. So as an intermediate step, we might have to calculate the electric potential first between the conductors. Once we have that, we can use this expression to calculate the voltage Once we have the voltage, all we have to do is to use the capacitor equation to determine the capacitance. And the capacitor equation says Q is equal to C times V. Capacitance is always a positive quantity. That was the reason why I wanted the voltage to be positive. Q is positive, voltage is positive, so you will get a positive capacitance. So if you solve this expression for C, what you are going to get is Q over V. Since we placed Q, we know what it is. We calculated V, we can get the capacitance. Now let's apply what we have learned here to one of the simplest capacitors, which is the parallel plate capacitor, and see if we can find out its capacitance. So we have our capacitor equation here, which we are going to make use of in our last step to determine the capacitance. But what was our first step? Our first step was to place the charges Q and minus Q on the conductors. So I will place Q on this conducting plate and minus Q on this conducting plate. And when you have two parallel plates with charges Q and minus Q, there will be an electric field between the plates from positively charged plate to the negatively charged plate. And we already know the magnitude of this electric field, which is sigma over epsilon 0. And sigma is our charge density, which is actually equal to Q over A divided by epsilon 0. So we are going to have the electric field, which is equal to Q over A times epsilon 0. And if you choose your x-axis in this direction, then our electric field will be in the positive x direction, and we can express our electric field as a vector as Q over A epsilon 0 I hat, where the negatively charged plate is x is equal to A and the positively charged plate is x is equal to B, and A minus B will be just our plate separation. Now we need to calculate the voltage, the potential difference between these two plates, and remember I want this guy to be positive, so I'm going to calculate V plus minus V minus. I am doing this because in these kind of setups, the positively charged plate will always be at a higher potential. Remember, if you go in the same direction as the electric field, you know that the electric potential decreases. So this is at a higher potential than this guy, which is going to be E dot dl from negatively charged plate to the positively charged plate. And I know that dl vectors in Cartesian coordinates is written as I dx, j dy, and k dz, but I'm not gonna even write the y and z components of the dl vector, because when I take the scalar product of these two, those will give me nothing. So if we continue with this, then E dot dl will be equal to, okay, let's just write it now. E dot dl will be equal to Q A epsilon 0 dx. Now this is an integral with respect to x. I can express my limits with the x coordinates, which is from A to B. Now these are all constants. We can take them out, which will give us the electric voltage to be minus Q over A epsilon 0. Inside the integral, the only thing left is dx, and the integral of dx will be just x with the limits going from A to B, which is minus Q A epsilon 0 B minus A, and B minus A will be just minus D. So the electric voltage is then Q A epsilon 0 minus minus will give you a plus times D. So we have our voltage. Now that all we have to do is put this guy in here to figure out the capacitance. So the capacitance is equal to Q over V, which is Q over QD over A epsilon 0. So the Q's will cancel out, and we are going to find the capacitance of this parallel plate capacitor to be epsilon 0 A over D. So this is the capacitance of this parallel plate capacitor. So when we look at this expression, we can easily see that the capacitance of this parallel plate capacitor does not really depend on the charge on it or the voltage across it, but it rather depends on the geometric aspects of this capacitor, meaning the area of the plates A and the plate separation D. There's another factor here, which is our constant permittivity of the free space. Now, if you want to increase the capacitance of this capacitor, what you can do is you can actually increase the area of the capacitor. But as with today's technologies, the circuits are getting smaller and smaller and smaller, so you can only increase the area so much. Eventually, it will become too big to be embedded in a given circuit. One other approach you can use is to decrease the plate separation here, but you can decrease this so much so that eventually you will have charges jumping from one plate to the other, and this is not something we want. There's actually a third possibility here, which is to change this constant. Can we change this constant? Well, the answer is actually hidden in the name. This is the permittivity of free space. So if we fill the space between the plates of this capacitor with some material whose permittivity is way larger than the free space, then we will have a capacitor with a larger capacitance. This is going to be what we are going to discuss when we discuss the dielectric materials at the end of this chapter. But for the time being, let's stop our discussion here and finish this video with a very simple example. In this problem, apparently we have a parallel plate capacitor whose plates have the area of 20 centimeters by 3 centimeters, and apparently these plates are separated by a distance of 1 millimeters. In part A, it's asking us to calculate the capacitance of this capacitor. In part B, it's asking us what would be the accumulated charge on it if it were to be connected to a 12-volt battery. And in part C, it's asking us to find the electric field between the plates when it was connected to 12-volt battery. And finally, in part D, it's asking us to estimate what should be the area of these plates if we want the capacitance to be 1 farad, keeping the same distance. So let's start with part A. Since this is a parallel plate capacitor, the capacitance is actually quite easy to find, which we found an expression for it in the previous board. So C is equal to epsilon 0 A over D, where epsilon 0 is 8.85 times 10 to the minus 12. This is our permittivity of free space, and the unit for that was Coulomb square per Newton meter squared. And we need to multiply this with the area, where the area is, okay, let's just draw a line here, 20 times 10 to the minus 2 meters. I need to convert everything to SI units, times 3 times 10 to the minus 2 meters again. And we need to divide this by the air gap distance, which is apparently 1 times 10 to the minus 3 meters. So if you calculate these, you are going to find the capacitance to be 53 times 10 to the minus 12 farad. If you want to use the engineering notation here, which is going to be then 53 picofarads. So we got our answer to part A. Now let's move to part B and calculate the charge stored on the capacitor when it is connected to 12 volts. And for this, we are going to use the capacitor equation, which states Q is equal to C times V. We just found our capacitance, which is 53 times 10 to the minus 12 farads, and I need to multiply this with 12 volts, which is going to be, if we were to pay attention to the significant figures as well, 640 times 10 to the minus 12 coulombs. Again, if you want to use the engineering notation here with the unit prefixes, it's going to be 640 picocoulombs or 0.64 nanocoulombs. So we got our charge as well on the capacitor. In part C, it's asking us to calculate the electric field between the plates. Now, if you remember the potential difference or the voltage we found in the previous board, we found the voltage to be equal to E times D. So if you use this expression to calculate the electric field, what you're going to get is V over D, where V is 12 volts and D is 1 millimeters, or 1 times 10 to the minus 3 meters. Then we will find the electric field. We will find the electric field to be 12,000 volt per meter. So this is the electric field between the plates. Here, as you can see, the unit for the electric field, we found it to be volt per meter. Up to this point, we were using newtons per coulomb as the unit of the electric field, but if you work it out, you can see that volt per meter and newton per coulomb are actually the same unit. Okay, let's open a new board and solve the last part and conclude this video. In part D, the question was to figure out the area of the plates if we wanted to have a capacitance of 1 farad. So we are going to make use of the same equation for the parallel plate capacitor, where the capacitance is equal to epsilon 0 A over D. This is 1 farad. We know what epsilon 0 is. D is known. We are going to solve this equation for A. So let's just do that. A will be equal to C times D divided by epsilon 0. So we will have 1 farad times 1 times 10 to the minus 3 meters. This is our D, and we need to divide this guy by 8.85 times 10 to the minus 12 coulomb squared Newton meter squared. So if you plug in these values in a calculator, you are going to find the area to be 1.1 times 10 to the 8 meter squared. So this is a huge area, and to appreciate how big that is, let's convert that to kilometers squared, which is going to be, by the way, 110 kilometer squared. As you can see, this is going to be a very large area to fit on a tiny circuit board. So with this, we conclude this video. In the next 2 videos, we are going to deal with the capacitances of a spherical capacitor and a cylindrical capacitor. And then we will move on to the capacitors that are connected in series and parallel. But for this video lecture, that's enough. You guys stay healthy, have a nice day, and we will talk to you in our next video lecture.